Now let's turn to repeated games. A repeated game is a game in which the same stage game is repeated t times. Player I's total payoff of a t-period repeated game is given by the sum of discounted one-period payoffs, where the future temporary payoffs are discounted at the rate of delta. Here, we multiply the total payoff by 1 minus delta just for convenience, and we will see why we multiply the total payoff by 1 minus delta shortly. Let's take a look at an example of repeated prisoner's dilemma, where prisoner's dilemma is repeated infinitely many times. The first thing to note here is that MM is the unique Nash equilibrium of the stage game here. Okay, and you should be able to verify this by now. Note here that UL gives a higher payoff to both players. And so these two players want to play UL and not MM if they could. And so we will see how we could support a subgame perfect equilibrium in which UL is played in every period. In order to support U and L played in every period in the subgame perfect equilibrium, we first divide the state of each player into two states, state C and state P. In state C, players simply take actions U and L. If player 2 deviates from L, then move to state P and player 1 chooses M in every period after and never go back to state C. If player 1 deviates from U, then move to state P and player 2 chooses M in every period after and never go back to state C. This strategy is called Nash trigger strategy, where each player punishes the opponent for deviating from the favored outcome. We now try to find a condition in which this Nash trigger strategy is indeed a subgame perfect equilibrium. We first check if player 1 has any incentive to deviate from state C. Note that we take the strategy of player 2 as given, and so we are not going to change player 2's strategy when we check if player 1 has an incentive to deviate. A more important thing to note here is that we only need to check if player 1 has an incentive to deviate in the current period by one-shot deviation principle. We do not need to check all possible strategies, which is not feasible in infinitely repeated games here. We can fix a strategy played in the next period onwards and just need to check if player 1 has an incentive to deviate in the current stage game. We first consider the total payoff of player 1 when player 1 follows the strategy and stays in state C in every period. Since the players choose U and L in every period, player 1 gets 1 period payoff of 5 in every period. Since the 1 period payoff is discounted for the future payoffs, summing across all the future temporary payoffs gives 5 times 1 over 1 minus delta. If you do not see how we got 1 over 1 minus delta, go back to the very first lecture of the course. Next, consider the case in which player 1 deviates from the strategy and plays M in the current period. Since any deviation leads to exactly the same payoff from the next period onwards, we just need to think of the deviation that gives player 1 the highest 1 period payoff in the current period. The deviation that gives player 1 the highest payoff in the current period is to choose M. If player 1 deviates to M, then player 1 gets payoff of 6 in the current period. Since both players choose M from tomorrow on, player 1 gets 1 period payoff of 3 from the next period onwards. Finally, we compare the total payoff under no deviation with the total payoff under deviation. That is, if the total payoff under no deviation is greater than the total payoff under deviation, then the Nash trigger strategy supports U and L in every period. By solving this inequality condition for delta, we find that the Nash trigger strategy supports U and L in every period if delta is greater than 1/3. Next, we check the condition under which player 1 does not have any incentive to deviate in a state P. Since M and M is the Nash equilibrium strategy of stage game, no player has incentive to deviate in a stage game. By one-shot deviation principle, we conclude that player 1 does not have any incentive to deviate from M and M for any value of delta. Next, we check deviation incentive for player 2. We first check the condition in which player 2 has no incentive to deviate from U and L. Again, we compare the total payoff under no deviation with the total payoff under deviation. If player 2 does not deviate, player 2 earns 1 period payoff of 6 in every period starting from today. If player 2 deviates to M, player 2 makes 1 period payoff of 4 in every period starting from today. And so it should be obvious that player 2 has no incentive to deviate to M for any value of discount factor delta from the inequality condition at the bottom of the slide. Here is a summary of the results about the conditions for Nash trigger strategy to support U and L as a subgame perfect equilibrium. We need to find the minimum value of delta that satisfy all the 4 conditions derived here. Therefore, the Nash trigger strategy is a subgame perfect equilibrium if delta is greater than 1/3.